We're going to continue our focus on the applications and of combs and potential applications. And we have another talk in this theme looking at the kind of the practical issues of deploying optical technology into space. And so our speaker is Mike Shao, and Mike is the principal research scientist in JPL's Science Division, and it's a great pleasure to have him here today. He's an expert in long baseline interferometry, and he's been involved in many of the systems, the big systems that we've read about, including Mount Wilson, 120-meter baseline interferometer at Palomar, the linking of the two Keck telescopes on Mauna Kea, and then also the technology development for the SIM mission, the Space Interferometer mission. Mike's current interests include actually detecting small, fast moving near-Earth asteroids from ground and space using CubeSats, and also the application of high-power lasers for ranging of orbital bodies. And so please join me in welcoming Mike. Thank you.
So I'll be talking about giving a couple more examples similar to the last talk on how to make things work in space. And so basically I'll talk about a couple of experiments that we did. One is a nulling coronagraph on a sounding rocket. And so what you heard from Carl was that sounding rockets those projects allow high risk, and so you know we'll show you what some of the risks were, and of course what's needed for an interferometer is precision alignment, thermal stability, and of course a surviving launch. And then I'll talk a little bit about the second topic, which is basically the lifetime of a NPRO laser that was to have been used on SIM. It has since that was the Class AB mission, it has a very high standard for reliability, and we'll talk about using redundancy in the pump system to achieve high reliability. So talking about the optical assemblies in space, basically this particular mission was a nulling interferometer. The idea, of course, is that the interferometer would null out the starlight so that you could see faint objects around it. And of course, what was needed what we wanted was something that was very thermally stable. The whole assembly should be no worse than twice as bad as an optical bench made entirely out of ULE. And so, and then of course that unit would be mounted behind a 50 centimeter telescope. And of course it has to be mounted in a way so that so when the temperature changes, it doesn't warp the optical bench. And of course, what was turned out to be the most challenging part of this was making the whole optical assembly survive launch loads. Actually, it's 12 Gs, not 20 Gs, random vibration between a few hertz and a kilohertz. And of course, the sounding rocket is a pretty rough ride into space. You also, in addition, have 9 Gs of static acceleration at the maximum. And so the other part of optical assemblies in space is that there are no micrometer knobs to adjust. And so everything has to be solid without adjustment. So what I'm talking, actually it's a 60 centimeter telescope, but only the central 50 centimeters is used. So this is sort of the sort of a drawing of the whole payload. It's pointed down during launch. In order to keep basically, so the telescope and then the nulling interferometer is in the back of it here, and I'll talk mostly about that. And in order to keep the sounding rocket basically goes up, and you have somewhere between 5 and 10 minutes above the atmosphere, and so you have very little time. And so in order to keep the the thermal stability of the telescope basically so that, well, the problem is that when you open up the door, you're now looking at 3-degree space, and so that's cold, everything radiates out. And so the way we tried to get around part of that anyway was that the mirror cover was cooled to 77 Kelvin at launch. And then, of course, the nitrogen was disconnected, and then it went up. And so when the mirror cover came off, essentially we were going from 77 Kelvin to 3 Kelvin rather than from 300 Kelvin. And so that helped stabilize the telescope. And then, of course, there were heaters and so forth to keep the instrument payload at a constant temperature. And so in order to keep everything, in order to keep the instrument stable, we decided to build the interferometer as a glass sandwich, and I'll show you what I mean by that. And so this is not a glass sandwich. This is the SIM beam combiner interferometer, and what you see is that the optics are mounted on an aluminum structure. And this was a brass board unit that actually went through flight qualification testing, and basically you can see it's fairly complicated. There are a lot of optical components in it. The structure, basically, the way JPL likes to do this, and it's moderately expensive, is that you start off with a solid piece of aluminum, and then you cut out 90% of it, and so it results in something that's very lightweight and very strong, but it's very time-consuming, very expensive. And typically, the way the optics are mounted is using these bipods that you see. Optics and optical assemblies are usually mounted using these bipods. Essentially, 3 bipods basically define 6 degrees of freedom. And so, if the thermal expansion of this is different than the thing it's mounted on, you will not distort the optical assembly or distort the optic. And so that's a standard technique using these bipods, flexures, for mounting optics and optical assemblies. So and of course this is a tried and true way of building fairly complicated optical assemblies, but for the sounding rocket experiment, it was also a little bit more expensive than we could afford. And I guess the other thing that we have to be careful about is because these flexure assemblies are they're all metal, and they have in something like this where basically the structural assembly is made of aluminum, it has a very high CTE, and the glass has very low CTE, and it's not, something like this on SIM, basically, in order to keep all the optics aligned, we actually, there were a number of optical elements that were on PZT tip-tilt mounts, and there was also a metrology system that monitored the alignment. And so it was actively aligned on orbit. And so that was also something that we wanted to at least partially get around in the sounding rocket experiment. And so the glass sandwich, basically, that we settled on was basically to put all of the optics in the middle. There would be a half-inch thick ULE plate on the bottom and a quarter-inch thick ULE plate on top, and everything would be glued between the top and the bottom. And you can see there are quite a few optical elements on there, and so the whole question, of course, is that you've got to put, and of course, since it's an interferometer, the optical paths have to be matched pretty closely, and of course, the tip and tilt of all the optics had to be aligned and basically be in the proper position when the glue sets. And so what we decided on was that, and of course, was to use very thin epoxy bonds, basically, at the top and bottom between the surfaces. Essentially, we have these things are about an inch, about 25 millimeters, and basically our feeling was that if the bond was only 10 microns thick, then then basically there's so little epoxy that even though it has high CTE, the whole unit would be fairly thermally stable. And that did turn out to be the case. And of course, the major challenge it turned out to be was getting a glass structure to survive launch. So the way the approach that we use for aligning the optics was that, well, a typical flight mount basically would have 3 of these bipods basically attached to the mirror, and then this would be an aluminum or titanium, mirror mount, and it would be held by 3 flexures to the optic. In our case, basically, to align these, it's actually very time-consuming, because if, for instance, if the tip tilt is wrong, what they did was they went in and they, by hand actually, basically filed the bottom of the mount so that it reached the correct tilt, and then and then tested it, and then if it didn't work, they would go back and refile. So it was a very time-consuming process. In our case, basically what we did was the optic was placed on top. First, everything was manufactured so that it was everything was manufactured so that the angles were right within a few arc seconds, maybe 4 or 5 arc seconds, and so that the vertical tilt was pretty close to begin with. And then, of course, it was sitting on top of a 10 microns of epoxy. And so what we did was we used a UV curing epoxy, and then we attached a rod to a PZT mount, and basically we manipulated the PZT until the interferometer told us everything was properly aligned. And then we zapped the UV curing epoxy with UV, and then the rod was bonded to the optical element with a very weak adhesive, so that just broke off. And so that was basically the procedure that we used for aligning all of the optics. And of course, even then, it does take a while. So it took over a month to align all the optical elements on that plate. So basically, this is the glass sandwich pretty much assembled. It was it was then held off of aluminum breadboard using 3 flexures again, and so. But basically, of course, what we said was the major challenge was showing that a glass structure can survive launch loads. And of course, before we did this, we built some prototypes that we tested on a shake table, and I'll show you what we did there. So it was not a full size, and of course, we didn't spend a lot of time aligning it. Basically, it was just 2 pieces of glass with some glass in between that we glued together, and and then we put the whole assembly on a shake table. The part of the sounding rocket program is that they provide these services for free, and so you can just ship it over to Wallops on the East Coast, and they'll shake it for you. And so on a project like SIM, we would go through a huge, a very detailed finite element model to figure out where all the resonances were, and we did that, but not nearly as thoroughly on a sounding rocket program. And so we knew where the principal resonance was, and basically it was in the flexures. And so the flexures basically bonded to the that had about 140 hertz resonance. It's pretty high, so it's actually pretty stiff, but so we did know about that, but we didn't fully, without really doing everything in detail. We learned by experimental testing. And so during the shake test, basically we had two iterations of shake tests, and we found 3 major design flaws in this, and I'll talk a little bit about what they were. And so this is trial and error engineering. So this is what happened on one of the shake tests. basically, see although the bottom of the table was shaking with 12 Gs, random between 10 hertz and a kilohertz, the accelerometers on the test piece basically recorded 200 Gs. And so that's basically because the resonant frequency, it was a high Q resonance. And so this is a common problem with using flexures on mounting optics, is that the flexures tend to have very high Qs. And so it'll amplify the G-forces that the optics feel. And as you can see in this case, it cracked the glass. The first thing that we found was that the UV cured epoxy is not nearly as strong as the flight approved epoxy, and so in fact some of the pieces actually delaminated. So basically, we after that we changed. We had to use UV curing epoxy in some locations because that was how we aligned the optics. But there were other places that were strictly structural features, and basically there we used the flight qualified epoxy. So the other problem was that was the high Q of the resonance. And so we reduced the Q of that resonance by using a thicker layer of RTV between the flexure and the glass. And so basically that damped out, that provided a damping, and basically after that, basically the maximum G-force is around 70 Gs instead of 200. And so that helped a bit. And then so the optics in the glass sandwich serve both as optical elements and structural elements in terms of supporting the top plate and the bottom plate. And so in addition to the optical elements, we added several pieces of glass that were strictly structural support that had no optical function. And basically that helped basically to keep the top and bottom plates together. And then the third one was we had departed from how we mounted the glass. In most of the glass elements were basically, that was the optical element, and then there was a 10 micron epoxy bond. In one instance, basically, we had actually cut out the bottom of it and put the epoxy there. So in this case, of course, epoxy shrinks when it cures. And so when this cured, basically, it pulled these two pieces together. And so in theory, this should be more thermally stable than that because there's no epoxy in the way at all. The problem was that at 250 Gs, it lifted off. So basically, this thing lifted off of those points that were no longer in contact. And of course, at 140 hertz, it meant that you were hammering two pieces of glass together 140 times per second. And that crack basically happened after about 35 seconds of vibration. And so we got rid of that and we went back to that. So those were the three design mistakes that we made, So of course those were the purposeful shake tests. The most challenging vibration and shock test was actually Federal Express. So some of you may have seen some YouTube videos of people throwing TV screens over the fence and things like that. So that something similar must have happened. Basically, we had noticed that the glass sandwich was actually there was only about 4 millimeters of clearance between an aluminum post and that glass sandwich. But we said, this is 140 hertz resonance. You need about 200 Gs in order for those two things to touch. And of course, we shipped it, and there was a small chip on the side when it arrived. But we decided that. So the team, we spent a couple of weeks discussing it. Should we take the whole thing apart, basically polish the glass out, so to get rid of the crack? And we decided that basically it was not in a load-bearing path. The crack was on the outside. There shouldn't be any loads on it, and so we decided to just leave it in place. and fortunately, that turned out pretty good. So, okay, but before we get there, so basically, we took, again, sounding rocket payloads allow you to take some risks. We had 2 shake tests. The prototypes broke on both of the shake tests, and then we made the corrections after the second one, and then it flew. Everything worked. This thing survived launch, and it survived the landing. However, the telemetry didn't work, and so that didn't work out. On landing, the nuller survived. The telescope did not survive. And what happened was that, BU was the lead institution on this. They had flown rockets before. I think they proposed and were funded for a reflight. The reflight is later on this year. And so hopefully we'll get some results from it this year. So once in space, the mechanical environment is extremely stable. And of course, for things like lasers and very high stability clocks, people might want to make use of that. And of course, at high frequencies, or at tens of hertz, basically, the noise that you have on a spacecraft is stuff that you bring up with you. And of course, something like the space station is particularly noisy because you've got people in there. And of course, this is you can go through a whole range of things. For the SIM mission, basically, a major source of mechanical noise on orbit, of course, are the reaction wheels. And for the SIM mission, basically, we used 2 levels of passive isolation, and that got the vibration levels down to about 10 nanometers. And so coincidentally, when we put the Keck interferometer, before we started building the Keck interferometer, we put accelerometers on the ground on top of Mauna Kea, and it was basically vibrating at roughly the same level, a few tens of nanometers. And so, seismic environment is similar to on the ground, is not very different from a spacecraft if you don't do something, if you don't do a lot more. There's, so if you want a much quieter environment than what you have in the lab, basically, then you've got to do some, you've got to have a non-standard spacecraft. One option is have no moving parts on the spacecraft and use gas jets for attitude control. That's what the Gaia mission uses. Another one that some folks have been looking at, but I don't think has actually ever flown, is to have a spacecraft with where the mechanical pieces that are moving are physically disconnected from your optical payload, and then they're linked with electromagnets and things like that to keep the positions in place. And then, of course, the most extreme version, or the drag-free spacecraft, used for things like LISA and things like that. And a number of GRACE and the gravity missions are doing that. Oh, the other type of noise, of course, is from things in low Earth orbit. Low Earth orbit is not a very benign environment because, especially if the spacecraft goes in and out of Earth's shadow, when the sun shines on it and stops shining on it, basically, there's a significant thermal shock. So the other topic I'll talk about is using redundancy to improve the reliability of the lasers that we used on SIM. So SIM was a Class AB mission with the 5-year primary mission with the consumables designed to last 10 years. So it's between 5 and 10 years. And SIM used an NPRO laser at 1.3 microns for its metrology. And NASA and JPL has a lifetime requirement that the laser would be good for 3 sigma over 5 years, and there would be a spare. So that means that the laser had to have a 99.7% of probability of lasting for 5 years, plus maybe 2 years while it's on the ground undergoing testing. And so we started looking into reliability issues around 2004 to 2007. And part of the reason was that JPL had flew an NPRO laser before that, a couple of years before that, on an FTS instrument, Fourier transform spectrometer, earth science instrument, and that unit failed after 2 years in space. And so, so we looked a lot at laser pump diode lifetimes, and basically and looked at how to use redundancy to increase the lifetime and reliability. So, so of course, you know, the SIM laser was at 1.3 microns, so it was outside of the silicon, so the silicon detectors wouldn't be able to detect it looking at starlight, so we wouldn't have to worry about scattered light from the metrology system. And we needed about 1 watt of pump power. And we would get about 200 milliwatts of 1.3 micron out. And so a lot of the laser diode lifetimes have mean time to failure of about 10 years, 100,000 hours. But of course that means that there's a 50% probability that it'll fail in 10 years. And so, and of course the probability of failure in 5 years is much larger than 0.3%. And so, so basically we needed, you know, the conventional diode pump, which probably would last 5 years, but you know, but in terms of having just a very low probability of failing in 5 years was not good enough. And so, so we looked into how we can increase that. So the plot on the upper right is sort of a generic plot of semiconductor devices. Basically, there's an infant mortality at the beginning, and then there's sort of random failures, and then there's, you know, when basically things wear out at the end. And so you can screen for infant mortality with testing, and usually if you're talking about things that lasting a long time, you never get down to this region. You're spending most of your time in here. And so, basically, there's the folks looking at semiconductor reliability have this formula, this model for basically they use it for accelerated lifetime testing. And so basically, the lifetime of the device is proportional to this, where these two numbers are determined by testing. And so, so essentially, you know, folks have tested laser diodes basically, you know, in terms of long lifetime tests, but just for the telecom industry. And you know, this one, the activation energy for most laser diodes is around 0.7 of an electron volt. And so, so basically, you know, this is used for testing purposes, but it also gives you some insight as to how to make the lasers last longer. And so, so there are a number of steps. One is, of course, using multiple laser diodes. Basically, you have to operate the lasers either in parallel or in sequence. As one fails, you turn another one on, with about a 90-year mean time to failure, and you know, increase from the 10 years that most of the diodes are rated at. And so it turns out that the simplest way to do that is to run the laser at lower power. And that model that in the equation that we showed before basically is that in terms of the total number of photons you get out of a laser diode, you get more photons, you know, total lifetime photons before it fails, by operating it below its rated nominal rating. And so, so they basically, that's one way of doing it. Of course, you know, at that time, back in 2007, you know, things are, of course, improved quite a bit now. That meant that we had to use multiple laser diodes to pump. And it was much more efficient, or we had to have far fewer laser diodes if we ran all of them at lower power rather than running one until it failed and then switching to the next one. And so the next is, you know, and of course, fortunately, it's fairly straightforward to do that. The NPRO laser basically has a YAG crystal, and you feed the pump in that way, and then the laser light comes out. in that direction. And just to move it a little bit ahead, basically the beam is sort of comes to a focus here, and then it spreads out. And so this is the red lines basically is the outline of the laser, and then the blue line is how we pump. And of course, this is single mode in red, and since we're pumping it with multiple lasers, it's got to be multi-mode going in for the pump. And so, you know, we get most of the overlap. The absorption depth is about 4 millimeters in the YAG for the pump beam. And so basically, we go in with a much larger, I think the laser is somewhere coming out between 50 and 100 microns in diameter at this point, and we're pumping in going at 200 microns. So we're wasting a lot of light here, but basically over here, and most of this overlap is most of the pumping is basically occurring not right at the entrance, but basically further on into the crystal. And so we looked at a number of different ways of doing it, and we finally decided to use 6 single mode lasers, and then there would be a beam combiner, a fiber beam combiner, and basically there would be a multi-mode fiber that basically would be then re-imaged onto the front of that YAG crystal. And so, so basically, part of the reason for doing this is that with a fiber combiner, you didn't have to worry about alignment. I mean, once it's attached, once the fibers are attached, you don't have to worry about further alignment. And so, in summary, basically, in building optical instruments for space, one should keep in mind, of course, the big thing is the launch loads, and in particular, the flexure mounts that are used to isolate stresses between things that have very different thermal coefficients of expansions. Very often they have very high mechanical Qs, and you've got to be aware of that, or else those high Qs can result in very high G forces on the optical elements. And but on the other hand, once you get into space, things are very quiet, and of course that's probably one of the reasons why you want to go into space for these very high stability clocks. And of course, the other part is thermal control. If you're not in low Earth orbit, thermal control is a lot easier in space than in the lab. Although it turns out that the thermal modeling is not quite as good as one would hope. Gaia is one example where they had originally designed the optical assembly to be stable to 30 microkelvin. And when they got on orbit, it was only good to 1 millikelvin. So things were off by quite a bit. They're not sure why, but still, I mean, something like that is, and that was, there wasn't too much active thermal control, but still. But if you're out of LEO, things are in general much more stable than you can get in the lab. So, and then the last point is that for active components, there are many ways of using redundancy to increase lifetime, and so. For a 3 sigma failure in 5 years, and then a full redundant, basically the mean time to failure for that is really many, many decades. So, okay, and that's pretty much it. Thank you.